This is the first in a series of videos concerning free body diagrams and how they apply to Newton's laws. And I'm gonna try to go slow. I want all my students to fully understand how to use these. They're such a powerful tool. As a matter of fact, they are really the only way that you can get your head around Newton's laws, and specifically that devilishly difficult third law. So in this video and in the next few, we will be discussing things like how to draw free body diagrams, why we need to draw them, what they tell us, and finally how to use them. So this will be divided up into several different videos depending on how long it runs. So buckle up and let's get after it. So how to draw a free body diagram. There are only two steps. Step one, draw a large dot for each object that you are analyzing. Each object will get its own free body diagram. A free body diagram is, at its most base level, the forces acting on one singular object. So if you have multiple objects, you will have multiple free body diagrams. One each. That is, if there's a book sitting on top of another book, sitting on top of a desk, you may have to draw 3 different free body diagrams to understand what's going on with all of those things. One free body diagram per object that you're analyzing. And then step 2, you draw and label arrows that represent the forces, and only the forces for that one object. You're not interested in forces acting on a different object. You're interested in forces acting on that object. Only forces. Do not, on a free body diagram, draw velocity or displacement or acceleration or anything else other than the arrows that represent the forces. So let's draw a few and we'll make some conclusions and a few more fine points about them. Here's one. Any object that has mass is going to have weight, so that is the force of gravity on it, so I just draw it pointed down with a W. If it is sitting on a surface, only if it's sitting on a surface, doesn't actually have to be sitting on a surface. If there's 2 surfaces that are exerting a force on each other, then you would have a normal force. I've labeled it here F sub n. Perhaps you have a string tied to your thing and there's some tension. Well, depending on which direction the string is being pulled, that tension could be in any of a number of directions. I picked this rather arbitrary direction, labeled it T. If you got more than one string, it might be T sub 1, T sub 2, that kind of thing. And then, assuming there's friction, you've got friction. Friction always opposes the motion, so whatever direction the motion is will be 180 degrees away from the direction of friction. Now, that's really all there is to it. We could have some other forces here. There could be, could be floating in water, could have buoyancy. We could take into account the friction of the air going past it. We normally ignore that. As a matter of fact, do ignore that unless I tell you specifically not to ignore it, or you can't ignore it. If it says something is traveling, falling at a constant velocity, that means it's reached terminal velocity, which means you cannot ignore drag, because it's the drag that's keeping it from accelerating more. But you might have drag on it. Any kind of external force, you might label F sub external. As long as you label these consistently in a way that I can discern, I count them as right. Now, one last point. We draw the arrows relative size. The arrow for normal force is the same length as the arrow for weight. That means, well, at least due to those forces, there won't be any upward acceleration. Because Newton told us to sum up the forces. Now, this odd little arrangement for the tension, that does look like it's going to cause the upward motion, the upward force, to be stronger than the downward force, which will cause some upward acceleration. Same thing is true with horizontal force. It might be that the thing has a net force to the right. Looks like it will be. In order to determine that, we have to take that tension vector and we have to figure out how much of it is being pulled up and how much of it is being pulled across. Students will recall the discussion in class about the students helping my wife, whose minivan had run out of gas, several pushing on the back and one rather inextricably pushing on the passenger side door. We figured out that the net force vector was off at some fairly random angle. Well, anyway, here's what you do there. If you had to, you would have to take the tension vector, find out how much of it was horizontal and how much of it was vertical, and then that would tell you if the vertical forces added up to 0, or the horizontal forces add up to 0. If they did, there's no acceleration on that axis. If they did not, then there is acceleration on that axis. Now, all that said, we have not yet handled this. We've not introduced trig into the situation, so we'll do that later. So that's all the rules. That's all there is to it. Drawing them should be very, very easy. I'm going to give you a couple examples from simple to rather difficult, and hopefully that should bring it all together for you. A book sitting motionless on a desk, it would have two forces on it. It would have its own weight pulling it down, and it would have the normal force of the desk pushing back up on it, pushing it up. It says it's sitting on the desk, which means it's motionless. Recall, we're not really so interested in velocity, we're interested in acceleration. Admittedly, they're related, but you can have something that momentarily has zero velocity, but does not have zero acceleration. Anyway, we'll handle that later. These two vectors, because it's motionless, they must add up to 0. That is, it being motionless and remaining motionless means that the acceleration is 0, which means the forces must add up to 0, and there they are. What if we were to do this? A book on a desk, no longer stationary, but being pulled by a string, and it says to assume there is no friction. Well, we draw the vector in, the force vector. There's tension on the string. Could have just as easily labeled that external force. That is force sub external. And now, still there would be no acceleration up and down vertically, but horizontally there would be acceleration because there is no way for this force to add up to 0. You've got to have two forces pointing in opposite directions, two or more forces pointing in opposite directions to get that happen. So let's assume that we don't ignore friction, and it would look something like this. There would be motion to the right, or that is, there's a force to the right, which means the friction would be, the friction would be pointed in the other direction. Now, problem didn't give us enough to go on. Is the friction vector shorter than tension, or the same length in tension? It can't be bigger than the tension, because the only reason it's there is because the tension is there. So we don't know. Maybe the problem's going to ask us to figure out what the friction is. If it said that it was moving to the right at a constant velocity, that would mean that these two vectors were the same, the tension vector and the friction vector. Those are tough to say together. Let's do another one, maybe a little more complicated. Here's one that could be a little tougher. Dude riding a bike up a hill. I say tougher. Not that tough. First I need my dot. Okay, we're there. Weight's a good place to start. I'm going to look at the guy and the bicycle as one object. If we wanted to, we could talk about the forces the guy exerts on the bicycle. The forces that are exerted on the guy and the forces that are exerted on the bicycle. We might learn something interesting, but let's not get crazy here. So that's the weight of the bicycle dude and his bicycle. Now there's going to be a normal force. Whenever there are two surfaces that are exerting a force, we call it normal, and it is always perpendicular. So I'm going to draw it perpendicular. Students tend to want to draw that straight up, pushing or pointing exactly opposite from weight, and that just is not the case. Now the guy's pedaling, so I've got a force here of him pedaling, and then it's possible there could be some friction at play here too. Now that is the free body diagram for this guy. The question is he accelerating, traveling at a constant velocity, or accelerating in the negative direction? That is he speeding up or slowing down? Well, you would need something more to figure it out. That is, I would need to know how long this force is for his pedaling. I would need to know what the weight is so that I could figure out how much of this weight is working against his pedaling and how much of it is working against normal. That is, we would resolve this W into its nice component like that, and then, well, we need to know this angle here, and this part of the vector that is the part that is perpendicular to the hill of the weight vector, would need to equal the force of the normal force vector, and then to determine if he's accelerating or not, it would be the force of impelling minus friction minus this part of the weight vector that lies parallel. If that points in the direction of the force of pedaling, he's accelerating. If it points in the opposite direction, he's still accelerating, but now it's a negative number. That means he's slowing down. And then, of course, it could be that they just perfectly equal out, and that would mean that he is traveling still, but now at a constant velocity. Okay, let me see if I can find one more that might be even more complicated. All right, how about this guy? I've got this some fool who's mountain climbing. I know there's guys that like that sport, but it never has appealed to me, even though I kind of like the daredevil things. Well, let's look. Doing these is just a matter of analyzing what's going on. Obviously, he has his weight pulling him down because gravity's working on him. He has some mass. Thank goodness there is a rope there, so there's tension in the rope. I've made the assumption that there's no one tied to the rope below him. I'm not sure if that's a valid assumption, but we're going to go with it for now. Now, those are the two obvious ones. Let's talk about one that's a little less obvious. Here, he is pushing on the rock. And that might strike you as a force. It is not. I mean, it is a force, but it doesn't belong on a free body diagram. But it's something he is doing to the cliff there. We're interested in what is being done to him, what force is being exerted on him. Now, when he pushes on the cliff, thanks to Newton's third law, the cliff pushes back on him. And when the cliff pushes back on him, then there is a force, and it would be perpendicular to the surface of the cliff. So it's a normal force. Now, admittedly, it happened over here, and I drew it right here on my free body diagram, on my dot. Turns out that physics was kind to us, and it doesn't matter where a force is applied, it'll have the exact same effect on an object. All right, that's almost all of them. There's one more. See his foot here? One can assume that he is pushing down on his foot, and there is friction there. That friction would be in that direction. That is, again, it's not what he's doing, it's what's being done to him. So he's exerting a downward force on the rock. That is causing there to be friction done to him upward. So we would take that and we'd represent it just like that. That, my friends, is the free body diagram for this rock climbing idiot. Now, you might wonder about his acceleration. Well, I tried to draw it as I think it would be true. The upward vectors equal the downward vector. There is no vertical acceleration. However, there is acceleration to the left in our picture, away from the cliff for him. That would need to happen at some point if he's going to finish climbing up that hill. So that's it for this video. Next we will see how all these, why we use them and how they apply to Newton's laws.